All right. Hello, everyone. I hope you can hear me. If I'm too loud or not loud enough, please just let me know. Otherwise, welcome to the last session of today. Before you have your well-earned rest with your free afternoon. My name is Sebastian. Most of you probably already know me or have seen me at the introductions on Monday, and I will be talking today about GPU performance engineering. And I am aware that this is quite a diverse crowd, so there will be probably some of you who will be a bit bored, especially in the beginning, because it's mostly repetition for them. Please bear with me. I hope it gets then more interesting and relevant for you towards the end of the session. And also, since I've been working in this field, I'm very familiar with all the technical terms and stuff like this. So if, especially to those of you who are not so familiar with GPU programming, if there's anything you don't understand, any term that you're not familiar with, please just let me know, interrupt me. I'm happy to explain that to you. I prefer that way over just repeating that term and you're sort of lost. Okay, so to tailor the session a little bit, I would like to do a very quick survey at the beginning just to get a feel for the room. So who of you already has experience with GPU programming? Okay, about half. That's interesting. Okay, we'll see. With CUDA or HIP? Okay, so this is the tech crowd. With SYCL, Open One API, DP++, whatever they call it. One, okay. OpenMP target offloading, probably the rest of you, hopefully. Okay. So at least if you have been to Ludovic's session on Tuesday, you should have experience with OpenMP offloading. OpenACC? Okay. Also good. And any other technology that I might have missed? So there are a couple out there. So what did you do?
Python, like Jazz.
Okay, yeah, perfect. That doesn't expose you too much to writing code, but you will still get something out of the session because you know how to structure your computation such that they map well to a GPU. All right, and?
I guess. I don't know if OpenGL counts.
Yeah, sure, OpenGL counts because you have to think in parallel as well. So you have, and writing an OpenGL program is not that different from writing a CUDA program from a perspective of how you encode your computations, right? Okay. Does any of you already have experience with GPU profiling? Okay. Okay, so for you it might be a bit basic, but I'm glad that there are some people here who have experience, because if I don't know the answer, then I know who to ask. Okay, so this tutorial will cover the basics of GPU performance engineering. The program set GPU performance analysis, but I tweaked that a little bit. And first of all, we will be talking about GPU architecture, because I could show you all these fancy tools and all the fancy traces and profiles and all the numbers. But in the end, for your personal work, this might be a bit overwhelming on the one hand. On the other hand, not so useful because you don't know how to interpret those numbers or relate it to performance in itself. We will then talk a little bit about potential bottlenecks. So what are you looking for when you do a performance engineering, and also how you can circumvent them to a certain extent. We will use, in order to do that, simple micro benchmarks. You will have access to them, and I will sort of guide you a little bit in how to write them on your own. And then finally, we will go into profiling tools and some hands-on example at the end, for which we hopefully have ample time. Okay, one disclaimer, this will not give you all the knowledge that is out there, of course. This is an introductory session, this is 2 hours. We will have to make certain sacrifices, and one of them is we will limit this to a very specific view, and this is the view that NVIDIA takes with NVIDIA CUDA. And we'll do this for 2 reasons. One is because the concepts that are used here are more or less applicable universally. So if you understand how an NVIDIA GPU works, it's very easy for you to map this to AMD GPUs and to Intel GPUs as well. And the second thing is that the hardware profiling tools that NVIDIA offers are, in my personal opinion, the most mature ones. They have been around for the longest. They're really well documented, they're stable, they're reliable, and especially if I want you to have a chance to play around with them, it's very easy for me to choose the tool which is less likely to break. That being said, if you know sort of what you're looking for in using the performance tools, because again, that's a tool, you need to know what you want to do with it, then you will also be able to translate that knowledge to the tools that AMD is offering, or Intel, or other vendors for that matter. Okay, that being said, let me go to my notebook. All the code is available to you. The link is on the Moodle. All right, so again, you have access to the repository. Let me just open it up. Again, the link is in the Moodles if you don't want to type this. There are a couple of things here. Okay, let me make this a bit bigger. Again, if you can't read something, please let me know, or check it out. So all the code examples, the slides, everything is included. We will be focusing mostly on the source folder. This is, as the name suggests, the code that we will be using for our experiments. And the profiles. This is all the measurement data that I obtained previously, and I did this for two reasons. One, because if all of you try to profile simultaneously on bridges, that is a bit of a bottleneck and can make this very difficult, let's say. So if you have the profiling data, just using that is streamlined in a sense. And also I included measurements for a different generation of GPUs, which you don't have access for today, which is the Ampere 100 card, sort of successor of the V100 card. It is included in bridges. And later on this year, when I get access to H100, I will update this as well to give you the opportunity to compare your performance results that you obtain across different cards and generations in particular. Okay, you can check this out by let me find my window, by doing a simple git clone whatever. You can do this on bridges if you want to have the code on bridges. You can do this on your local laptop if you want to have the profiling data on your local laptop, and if you want to look at the source code on your local laptop. I recommend the second option because that gives you a smoother experience than doing this remotely. Okay, we'll be coming back to that in a second. Okay, so first of all, let's talk a bit about GPU architecture. And we've seen a bit of this throughout various sessions this week. Okay, before we go into architecture, I want to motivate a little bit why we are going into architecture. And again, we've seen this throughout this week, and we also heard a bit of the motivation behind it. And the one thing is that GPUs offer this massive performance and parallelism, and also good energy efficiency. And they're quite widespread. You've also heard about this already, so this is just a repetition. In the top 500 list, there's plenty of GPU-equipped machines, and in particular in the top 10, 90% of those are already equipped with GPUs. Majority of those currently is NVIDIA, again, further motivating the choice for this session. And the question for us is, where does the performance come from, and how can we use that performance, and when do we know that our code is actually using close to 100% of the performance offered by the GPU that we have available at hand. Okay, and architecture-wise, there are two main contributors. So first of all, we have a massively parallel computational throughput, meaning we can do a lot of computations in parallel at a high speed, moderately high speed compared to CPUs. And this is what you're interested in, because this is giving you the speed that you can do your meaningful computations in. As an application scientist and also as a computer scientist, this is what you're looking for. However, in practice, you're frequently also restricted by the speed of getting the data that you need for the computations to the units doing the computations, and to storing the data back after doing the computations. And here we are usually speaking about main memory bandwidth, the bandwidth that we use to get and store data. And on GPUs, you will find that this is comparatively high compared to CPUs. So either your code, ideally your code should either be bound by one of those factors, and both of them can be done well by the GPU. And the question is, why is this the case, and how good exactly is a GPU? And for this, I want to give you a bit of a more technical view on one of the more recent ones, and this is the H100. I deliberately chose not to do the V100 or the A100, but the newer Hopper cards, to give you a feeling of what is out there currently and what you could buy if you would have the budget. So this is, I think, around 35,000 euros, pounds, not pounds, dollars. So it's pretty expensive. But if you have access through your local compute clusters or national compute clusters, then it's a nice tool to play around with. And again, so we've seen the schematics. This was what I was originally getting at throughout this session. And I want to give you a bit more the technical view. So this is taken from the white paper from NVIDIA. So this is what they advertise. The white paper itself usually is published, or they publish a white paper for each new generation of GPUs. It's a good read. It's usually about 80 pages, let's say. There's quite a bit of marketing in there, but also a lot of technical information. And one of them is how they structured their GPU. And I don't want to go too much into detail here, just showing you that GPUs are in essence very complicated and very complex, and that a lot of effects that you can see with the profiling that we do later on are attributed to that complexity. I also want to show you that in essence everything on the GPU, or most of the things on the GPU, are structured in a certain way of hierarchy, in a certain hierarchical fashion, and that we need to understand that hierarchy and how our software maps to that hierarchy to actually get performance out of it. And I'm introducing some terms here and also tell you which are important. So first of all, a GPU is subdivided into graphics processing clusters, GPCs. These are further subdivided into texture processing clusters, TPCs, and these are further subdivided into streaming multiprocessors, SMs. SMs is the level of abstraction that we want to think of in. The rest is sometimes important. This is why I mention it here. For like 1% of the cases, maybe. In virtually 99% of the cases, SM is the unit of abstraction you want to think in. And this also relates to what Ludovic has been telling you yesterday. This is where your teams, or if you're coming from a CUDA background, your CUDA blocks will be scheduled. Okay, now I've shown you this fancy picture. NVIDIA will tell you this is theoretically what a GPU would look like, but it's not really what you're getting. And what you're getting is a bit more of a mixed bag. You will get 8 of these GPCs, but each of those GPCs will have a varying number of TPCs. In this generation, it would be 8 or 9. And again, varying from GPC to GPC. And each of those will have 2 SMs. And in total, a full H100, such as the one you can buy, will have 132 SMs. Why is this important? Because our parallelization needs to match this to a certain extent, and we will see this later on. Okay, now going even further down the hierarchy, we are now looking at a single SM. Hopefully you can see this. You don't need to read it just to see that this is again hierarchical. So each of these SMs is again partitioned into what is called an SM subpartition. And now finally, these subpartitions have the units of execution that we're interested in. So these are really the hardware units that are doing the computations that you are interested in. And in particular, each of these 4 subpartitions has a number of int32 units. So these are the, let's say, cores, in quote unquote, that are doing your int32 operations. Most likely in your code, this will be index computations. Then there is a number of FP, or single precision floating point execution units, 32 in total, and a number of FP64 execution units, double precision floating point units. Why am I telling you this? Because you need to know what your code is doing, or in which precision and which data type it is doing its calculations, such that you can figure out what the performance is that you expect. So for this GPU, you can see the number or the ratio between FP32 and FP64 units is 1 to 2, meaning if you switch from single precision to double precision, you lose, in a sense, half of your computational performance. This is not because you did something wrong with the implementation. It's just a feature of the hardware. And this is sort of for HPC cards. As you probably know, for gaming cards, this is even worse. So this ratio will not be 1 to 2, but more like 1 to 32 or 1 to 64 in the extreme case. Okay, so let me defer that question a little bit when I talk about the parallelization and how this maps to the execution units, and then I can answer that. If I forget, please let me know. All right. And sort of as a side note, if you read the CUDA more marketing-focused documentation, these will tell you about CUDA cores. This is sort of what is advertised, and usually this refers to the FP32 units. Side note 2, in this architecture, the int32 and the FP32 units are separate, meaning you can do your integer computations and your floating point computations simultaneously. That's not the case for all the architectures. So if you have a code which does a lot of index computations and a lot of floating point computations at the same time, then this can result in a slowdown on an architecture where this is using a shared hardware resource. So it makes sense to look at this hardware again to relate this to the code that you're running on it. Okay, and oh yeah, more recently there were also tensor cores introduced into this architecture. There is only one per subpartition, but this one core can do 512 FMAs at the same time. I'm assuming you're all familiar with FMAs because this has been noticed or used as a term throughout the sessions. If not, this is a fused multiply add, meaning it's a multiplication and an addition in one single instruction. And this is also let's say the instruction or the way of computing that gives you the highest performance. So each of these little cores that you can see here, I call them cores again, quote unquote, can do one FMA, meaning if you're doing only multiplications, you will still get the same number of instructions as throughput, but only half the flops. If you're doing only additions, you get half the flops. If you're doing only FMAs, you get the full performance. Speaking of performance, so just to give you a feeling how NVIDIA or all the other vendors as well calculate their peak performance and what you can expect, you can calculate this very easily by just taking the number of cores, so again, cores in quotes, factor in a superscalarity. For GPUs, this is not so important, but if you want to relate this to CPUs, this would be a factor different than 1 for most modern CPUs. An FMA factor, so again, one instruction does one addition and a multiplication at the same time, so these are counted as 2 flops. A SIMD width, we can either, okay, let me talk about this in a second, and the frequency. The SIMD width, if you're familiar with CPU computation, is related to the vector intrinsics and vector execution units. And now we have different ways of viewing the execution on a GPU. Either we take the full amount of cores that we just calculated the slide before, so 16,000 cores or 17,000, and each of them can do one FMA with around 2 gigahertz a second, and this results into around 67 teraflops a second. We could also take a more SIMD-focused view, so again, a bit more technical. If you're coming from the CPU side, this might look familiar, and say, well, we have these 530 or whatever subpartitions, and each of them can do 32 operations at the same time. Why is this important? Because the GPU more or less works similar to a SIMD machine. Okay. This is the compute. Of course, again, you need to get data to do computations on as well. So each of these SMs features a couple of registers. So these are it's a very fast memory where you store all your intermediate results, all your variables. And then they feature something that is a shared L1 cache and shared memory. If you're familiar with caches, great. If you're not familiar with caches, this is a very small memory which usually gives you really high performance, and it is used to buffer or store data that you access repeatedly. So this is something that the runtime will do for you. This is all, in a sense, implicit. And the shared memory is sort of the explicit counterpart. So this is a small memory that you as a programmer can use to buffer data and to exchange data between different threads running on the same execution unit, in this case SM. Shared across all the SMs is a bigger cache, which is available to the whole GPU. Again, buffering all the intermediate values and the values that you access repeatedly. And then there's a main memory behind that. This is the one where your data usually comes from. In terms of sizes, let's start at the bottom. So for the H100, we would have 80 or 96 gigabytes available, depending on which version of the card you're actually buying. And this will deliver a bit over 3 terabytes a second. So this is massively fast, can get a massive amount of data to your SMs.
Above that is an L2 cache with 50 megabytes. So you can see the relation. This is sort of 3 orders of magnitude less. So it's a very scarce resource, but it's in terms of bandwidth faster. And on the H100 and also on the A100, this will be split into 2 subpartitions again. So you again see the hierarchy. You don't need to care about that too much in terms of programming, but in terms of performance, sometimes you see effects relating to that. And then for the L1 cache and the shared memory, this will be even smaller with 256 kilobytes, but it's sort of not that bad because this is per SM. Remember, you have in the order of 100 SMs. So if you multiply this together, this is still around 25 megabyte. And then there's some registers, again, in sort of the same order of magnitude. All right, and of course, as you know, GPUs are only part of your system, so there are other things that might be limiting your performance. One of them is the connection to other GPUs, and the other one is the connection to the host itself. You've also learned about this in the OpenMP session yesterday, at least the CPU part. And the reference sort of here is the main memory bandwidth. So remember, this is the speed with which we can get data from the main memory to our execution units. And now we can compare this to the different data paths of our system. And one would be the PCI Express connection, connecting the CPU and GPU. And that would give us 64 gigabytes a second. So you can see more or less a factor of 2 orders of magnitude less. So if you're doing these kinds of transfers from host to device frequently, this will kill your performance in a sense. And this is also something that we want to look out for later. Between GPUs, if that's available on your cluster, is a proprietary solution called NVLink that accelerates the transfers a lot. And for this generation, this will give you 450 gigabytes a second per direction. So that's still about an order of magnitude less, but it's not as bad as the PCI connection. The good news is if you're using stuff like MPI, and if it's configured and compiled correctly, then MPI will figure out that this NVLink can be used to move data between the GPUs in your system, and will take that faster data path. Okay, so just as a comparison, so the V100 card, to show you sort of the trend where everything goes in the HPC community. The V100 cards, that's the one in bridges. The A100, that's the one that's widely used in many compute clusters, let's say, and the H100 is sort of the newer card that is slowly being established into the compute clusters around the world. We will see that the number of FP32 cores grows rapidly. So not so much from Volta to Ampere, but substantially to H100. The number of SMs, not so much. So this would be 80 to 108 to 132. But the teraflops, of course, grow more or less alongside the number of cores. So with the V100, we get 16 teraflops, which is still pretty good, up to almost 70 with the H100. For memory, we see a similar trend, so everything gets bigger. So for the V100, we had 32 gigabyte, which is, if you're doing AI, probably not a lot. And for the newer H100 cards, this goes up to 96. And for the cache, the same thing. Don't want to bore you too much with the details. And for the bandwidth, you can actually see a substantial increase every year. So this is also why I'm telling you about the H100 card in detail, because in 2 years this will probably already be outdated, but it will still be sort of close to what is coming up. If I'm talking about the V100 card, you know that this is not going to relate performance-wise too much to what you have available today and in the next years. Good news is PCI is also getting faster, about a factor of 2 every generation, at least in this case. And NVLink is also getting faster linearly. All right. The sort of flip side of that, your TPD goes also up, so the amount of energy that one of these GPU consumes. So the GPU itself is getting bigger, but also the energy consumption is. And you can see there's sort of a similar trend, excuse me, a similar trend, unfortunately, in the TPD as well. All right, so why am I telling you all of this? Because if you understand the way the GPU operates, this gives you sort of half of the story of where the performance is coming from and what you have to look out if you measure and engineer that performance. The other half of the story is the parallelization and how it is mapped. You've learned, if you have been to the OpenMP session, that the threads are organized in teams, which are then distributed, in a sense, onto the SMs. If you're coming from a CUDA terminology, then you're familiar with the same concept, but different terms. In CUDA terminology, you will have threads similar to OpenMP, which are organized in blocks. This would sort of be the equivalent to the team, which are organized in a grid. One side note, OpenMP is very flexible in its standard, so that this is in a one-to-one mapping is not guaranteed. The compiler is free to choose that, however they want to do it. Usually, teams get mapped to blocks, but again, there's no guarantee that this is actually going to happen. Okay, and why is this done this way? Again, because the hierarchy of parallelization maps very nicely to the hierarchy of hardware that we have. So each of these, in OpenMP speak, loop nests or target regions gets executed on a single GPU. All the teams or blocks inside get mapped to the SMs, and all the threads inside get mapped to the execution units. And then there's one last bit of information I have to give you, that all of these threads inside a block or a team are grouped into what NVIDIA calls a warp. And on virtually every hardware, this is 32 threads. On AMD, it's 64, but on all NVIDIA hardware, it's 32. And why am I telling this? Because these threads will be executed in tandem. And that means if some of these threads are doing something different than the other, that might be a bad idea. If you are not having 32 threads to fill up a warp, that might be a bad idea, and so on and so forth. And to come back to the question from before, so if you have something that is not, or if you have a number of execution units that is not equal to the size of a warp. So let's say you have 16 or 8 or just one execution unit. Then the threads will have to, first end threads will start the computation and the others will be stalled. So they will wait for their turn, and then once it is their turn, they will execute. These will be happening in parallel. For most hardware, they will, yes.
Not in different warps. In one warp, you will see for the quick operation
Ah.
and like the
No.
in and then, the 32 float.
That's a good question. So you would have to look into the assembly code and also an in-depth profiling. So can't tell you that right now from the top of my head. But let's discuss this later. This sounds like an interesting topic.
So don't all the threads in the warp execute the same instruction?
Ideally they do, but 2 or 3 generations ago, something called warp divergence was introduced, and this allows threads in a warp to diverge in their control path. Meaning that if you don't explicitly synchronize them, you can't be sure that they're in the same instruction. Make sense?
So,
Yes. Or none. All right. Okay, sort of this was more or less the heavy lifting. Now we can relax a bit and try to use that and talk about performance modeling in general, write a bit of code and execute this and profile this. Okay, so in performance modeling in general, what are we looking for? We're looking for relevant metrics in relevant code regions, and we've heard about this in Ilya's talk this morning as well. What are relevant metrics? Usually it's time needed to execute that code region or time to solution. But it can also be more in-depth, such as bytes read or written, floating point operations performed, and so on and so on. And what are relevant code regions? Now, this is a bit more problematic, because usually when you start, the whole application might be your region of interest, because you don't know where you want to focus on. And later on, when you have a more clear view of how runtime or execution time is distributed onto the parts of your code, you can zero in into different kernels, functions, loops, or otherwise defined regions of interest. Once we obtain those metrics, we try to relate them to our theoretical limits and express them in terms of observable performance to see whether we actually hit the limits that the hardware imposes on us. And then we try to figure out where we can optimize and whether that optimization is reasonable. Because if we are at 90% of what is possible, maybe an optimization doesn't really make sense. Okay, so again, these are the 3 steps, and tools can be a great asset in that, which is why we will be talking about those in a bit. Let me look at the time. Okay, perfect. Okay, so before we head into tools, we want to talk a little bit about micro benchmarks. Because usually when you start investigating the performance of your big application, your big package, you don't directly dive into profiling everything, because this will give you a mix of a lot of different effects. You usually try to break this down to something that is easier to investigate, and at the limit you can break this down to something that is only a very small kernel function or loop, or however you want to look at it, which gives you the ability to see how under ideal conditions that part of your code would perform. And this is exactly what we do with a micro benchmark. And I said in the beginning, usually the bottleneck should be, under ideal conditions, either the compute itself or the time getting the data that we need for the computation. And these are the 2 things that we want to benchmark here. You have the code available as well. If you want to run this code on bridges, one thing I want to mention, please use exactly that version of NVHPC. So the module system on bridges is a bit, can be a bit difficult. That version works for OpenMP, it works for CUDA, and it works for the profiling, which is sort of not the same for many of the other versions that are installed there. Okay, that also means if you have adapted your bash RC in Ludwig's session yesterday, you would have to revert that change. Okay, but there's no need to run anything, so this is just sort of documentation, let's say. Okay, before we actually run this, maybe let's have a look at the code itself. I have included a couple of versions. There's usually one base version, so this is a serial CPU implementation. It's meant to be very easy to read. If you're familiar with C++, sorry for that, so I don't include any Fortran examples, unfortunately. Nevertheless, the code is very flat, so it should be easy to make out the relevant parts. And then an OpenMP CPU parallel version, just to compare against. An OpenMP target offload version, which should relate to sort of what you've learned in the session yesterday, and a CUDA version for those of you who are a bit more seasoned GPU programmers. And for the computation, we do something very simple. We just repeatedly spam fused multiply adds and take the time it requires to do all of that and use this to approximate our computational throughput. So for the CPU version, we do this for a given problem size. This is the loop that we will later parallelize with OpenMP or map to CUDA. We do this in a local variable. We just read in a value to prevent the compiler from doing fancy optimizations, because depending on your type of computation, it's very easy to write a code that the compiler will optimize to a certain extent, and then you will do less operations than you actually anticipated. This is part of the reason to prevent that. Then for a number of repetitions, by default, we will be choosing 1 million. We'll just do a fused multiply add and override our local variable again and again and again. And then again, to prevent the compiler from optimizing all the computation away, we store the result. And that's basically it. That is our region of interest. This is the representative kernel of whatever we actually are interested in or what we want to investigate. If we scroll down a little bit, there's more boilerplate code. I don't want to go over too much. I'm just telling you sort of the key points that you usually find in such codes. There is some command line argument parsing, just such that you can configure this from the command line and also put a script, wrap it around it to do this for different problem sizes or whatever. There's some memory management. For CUDA, this will also include device memory allocation. Some initialization, so usually you try to figure out a way to initialize data such that you can track whether all the computations have been done successfully, because you only want to benchmark applications that are actually doing the right thing. And then what is not always included, but which makes sense to include, is a warm-up iteration. So we're doing the same thing that we want to do later on, but we're not timing it yet. And this fills the caches and allows the hardware to choose an appropriate frequency of operation if that's necessary, and other things. Usually this is a very low number, so 1 or 2 usually suffice. And then once we've done this, we do what is actually relevant. So we start a measurement. Here we're just using standard chrono. Could be anything else as well. Could also be your marker for your favorite profiling or tracing tool. Could be, MPI time, OpenMP time, whatever you're comfortable and familiar with. Then we do the same thing that we want to profile repeatedly over and over again to get an averaging effect. And also to eliminate the influence of overhead. And then we stop our timing. We print some stats. We will see how this looks like in a second. And then important, we check the solution, so whether all the values have been computed successfully. For reference, the OpenMP host version, I won't show you the CUDA version because I imagine if you're a CUDA programmer, you know how to translate this to CUDA. If not, the code is available. If you find a bug, please also let me know. If you're, sorry, that's the host version, the target version. If you've been to the session yesterday, you know that you need this sort of black magic, quote unquote, invocation with all the right parts in it. And you need to spawn all your teams. You need to distribute the workload onto those teams. And then you need to parallelize the workload inside the chunks per team onto the threads, which is exactly what we do here. Otherwise, it's the same code. So it's just that one pragma edit. And further down, we will find, maybe I can get this on one screen, a target enter and a target exit. Again, this is the same thing that you've discussed yesterday. It's not performance optimal, let's say. So you probably spotted that some of the transfers could have been eliminated. I did it this way because I can make sure that I'm overwriting all the values that I want to overwrite. So I know exactly what will be in the buffer before I do my computation, also for the output buffer. Of course, you could now also have a regular data region without this enter and exit. That's just personal preference because it maps very nicely to the CUDA mem copies that you frequently see in the CUDA code. Okay, and that's sort of it. Sorry for that. Let's try to run this. So first, let's try to make it. And again, if you've been to the software session, neither my make files nor my Git repository are up to any software quality standards. So virtually every step of the way is a bad example. Please don't do any of this. This is sort of just to make it easy for you to try it out and easy to reproduce. Okay, as you can see, we will just use GCC to compile this. We use the NVC++ to compile the OpenMP and the CUDA stuff. Should be pretty standard. And then I also included a bench target, which does a simple benchmarking, meaning it just runs the code a couple of times. And the relevant things that we can see here are a couple of metrics. So depending on your application scenario or application background, you will either think in mLoops, in bandwidth, or in computational throughput, usually. Of course, there are more specific metrics as well, but these are the things that are usually important. If you're not familiar with those, that's fine. But at least the bandwidth and the compute should be familiar by now because I've talked about them for like 40 minutes now. Okay, and as you can see, we get about 15 gigaflops, which is pretty close to what the peak performance says. I think this was about 16, 70 gigaflops for the Volta cards. So our benchmark, in essence, works. It gives us a good estimate of what we can expect, and it also shows us we're not reaching the theoretical peak performance. And it quantifies by how much we're off. And even better, it shows us this for the parallelization approach that we've chosen. So this is exactly tailored to OpenMP target offloading or CUDA or whatever you implement this in. And you can tune the number of threads and your virtual problem size to what you're interested in. So if it's a way bigger or way smaller problem, this can be accustomed here. As you can see, we just ran this with a pretty standard or pretty arbitrary, let's say it like this, number of threads, which is giving by 1 million. Short side note, for the CUDA version, if you're familiar with this, this is using a grid stride loop, so this might not be equivalent to the number of threads, but will give you the number of thread executions. Okay, and again, there's a result check at the end. For the stream, for the stream, we're doing in essence the same thing. We just have a different kernel that we time. So instead of doing FMAs, we just do a simple copy operation and simultaneously increase everything by 1. This 1 gives us a flop rate as well, because we're doing 1 flop now. And second, it gives us a way of verifying that the copy operation has been done successfully for a number of times. Again, this is just to check whether our simple benchmark is doing the right thing or not. If your background is computer science, hopefully this looks a bit familiar. All right, so let's try this out as well. Oh, sorry. Okay. And this is running this on CPU and GPU. For FMA, I didn't run it on CPU because it's horribly slow, and I didn't want you to wait too much. You can still do it. It's in the makefile, just comment it in. And now what is important is not so much the compute, because that's abysmally low. We already expected this, but the bandwidth. And for the CPU serial version, we can see we're at about 11 gigabytes a second, which is still not good. So on this system, it's probably not a good idea to use the CPU serially for some memory-intensive operations. If we're adding OpenMP, this gets a little bit better with close to 40 gigabytes a second. But once we switch to the GPU, this really kicks off with close to 800 gigabytes a second. The theoretical limit here was, I think, around 900 gigabytes. So we're still a bit off of that, but this is sort of the point of this benchmark. So we want to see under actual conditions for an actual data access pattern, what is the bandwidth that we can expect. And in practice, the bandwidth is really highly dependent on the number of input and output elements. So how many vectors you read and how many vectors you write. Here we had 1 read and 1 write, which is not an ideal case, which is also why we are quite a bit away from the theoretical peak performance. Takeaway for you, it's important to adapt this benchmark to the pattern that you have in your application. So if your application is reading in a lot of data in the kernel, but only writing very little, then you need to reflect this here. And then you will get a different sort of measured peak performance than for this benchmark.